For the past 2 years, the James Webb Space Telescope has been finding monsters that shouldn't exist. Black holes so catastrophically huge, they threaten to break our entire understanding of the cosmos. They are too big, too early. It's like finding a fully grown skyscraper in the middle of prehistoric Earth. For years, physicists thought the universe itself was broken until a new study revealed we might have been fooled by a cosmic illusion. The illusion didn't come from the black holes themselves. The measurement was the problem. A paper published in June 2026 in Astronomy and Astrophysics by astronomer Alessandro Trinca and colleagues made exactly this case. They went back to 14 of James Webb's most notorious early universe black holes and found that the same data fits 2 completely different stories. In one, the black holes are genuine giants, but almost completely dormant. In the other, they are far smaller than thought, and they are not dormant at all. They are feeding at rates that shouldn't be possible, rates that make them invisible. But how do you hide something that massive? And why would feeding too fast make a black hole harder to see? You cannot weigh a black hole directly. You cannot orbit one. You cannot send a probe anywhere near it. What astronomers do instead is watch the gas spiraling toward it. Gas moving so fast, its light stretches into a characteristic pattern called a spectral line. The broader the line, the faster the gas. The faster the gas, the more massive the black hole pulling it. This method has been the gold standard for decades, and under certain extreme conditions, it is profoundly wrong. Every feeding black hole has a theoretical speed limit called the Eddington limit, the point at which radiation pressure from infalling material pushes back so hard it stops more matter from falling in, like a fire hose turning on itself. For generations, astronomers assumed black holes fed near this ceiling, not because the physics demanded it, but because nothing they'd ever observed suggested otherwise. Safe assumptions are the most dangerous kind. So what happens when a black hole doesn't approach the Eddington limit, but blows straight through it? When a black hole feeds at what physicists call super Eddington rates, far beyond the theoretical ceiling, the gas around it stops behaving normally. Instead of settling into a thin accretion disk, it puffs outward. It inflates into a dense, turbulent shroud of ionized gas, thick, chaotic, almost opaque. It corrupts the spectral signal, the very measurement astronomers use to calculate mass. The shroud adds its own turbulent velocity to the light passing through it. And when you feed that distorted signal into the standard mass formula, the answer is not the mass of the black hole. It is the mass of the storm. The black hole has wrapped around itself. And here is where it gets darker. Because Trinca's team didn't just theorize this, they tested it. They built a new tool designed to pit both possibilities against each other directly, then fed in the data from 14 of James Webb's most puzzling early universe black holes, one by one. The result? For every single object in the sample, both stories fit. Neither could be ruled out on the numbers alone. What separated them was physics, a smaller black hole feeding at extreme rates, hidden inside a self-generated cloud absorbing its own X-rays. That is something we actually observe elsewhere in the universe. A truly massive, dormant object producing almost no light at any wavelength is not. But the strangeness of this problem goes deeper than a single paper. Because there is a second clue, one that had been sitting in the data for years, refusing to be explained. If these early black holes were truly as massive as the standard formula suggests, they should be screaming in X-rays. Every black hole that size in the nearby universe does exactly that. We've catalogued them. We know their signatures. James Webb's early universe black holes are almost completely silent. That silence was a loose thread no model could tie off until the Super Eddington picture made it snap into place. When a black hole feeds at extreme rates, it absorbs most of the X-rays before they can escape. The hole isn't quiet because it's inactive. It's quiet because it's hidden inside its own hunger. James Webb has now catalogued roughly 300 objects known as little red dots, compact, faint, intensely reddish sources scattered across the young universe, each one hosting a black hole no existing model could explain. If this picture is right, many are not impossibly massive objects. They are smaller, faster-feeding black holes mimicking the spectral signature of giants, their true size hidden behind the same ionized veil. 300 objects we misread, and we only found them because we built a telescope powerful enough to see back to when the universe was less than 1 billion years old. If the measurement is broken for these objects, it may be broken for the ones we thought we understood best. Ton 618, somewhere between 40 and 66 billion solar masses. Two major estimates that differ by nearly a factor of 2, both derived from spectral line widths. The same technique this paper calls into question. Or the black hole at the center of the Phoenix cluster, sometimes cited at 100 billion solar masses, a number scientists are still arguing about, with newer work placing it considerably lower. Here is the uncomfortable truth. Almost every mass estimate for the largest known black holes relies on the same family of indirect measurements: spectral line widths, gas dynamics, stellar velocities. None of these methods directly weigh the black hole. All of them involve assumptions that may be wrong under extreme conditions. To be clear, Trinka's team looked at black holes in the very young universe. They didn't prove that nearby objects like Ton 618 are distorted in exactly the same way. But what it does prove is this: the way we measure black hole mass has a real blind spot, and we don't yet know how wide it is. Every cosmic record you have ever heard may carry an asterisk we haven't written yet. Think about what that means. For years after James Webb's first discoveries, the scientific community seriously debated rewriting cosmology. Not tweaking it, rewriting it, questioning whether our models of the Big Bang, of how structure forms, of how fast the universe can build things, were fundamentally broken. The universe hadn't broken anything. We had mistaken the signature of extreme hunger for evidence of extreme size. The signal wasn't the black hole, it was the storm. It had built around itself. And here is what makes that genuinely unsettling. We were so certain of our instruments that we were ready to tear up a century of cosmology rather than question the ruler. The black holes didn't fool us because they were clever. They fooled us because we forgot that every measurement is only as good as the assumptions behind it. The black holes weren't impossible. They were lying, not out of malice, but because we were reading the wrong signal. James Webb continues to observe, building larger samples, longer exposures. But whatever it finds, something has already shifted. We live in a universe so vast that even its most extreme objects can hide from us, wrapped in their own energy, invisible to the very instruments we designed to find them. If the brightest things in the cosmos can deceive us, we should hold every certainty with slightly looser hands. Every record in astronomy is a photograph taken with imperfect light through imperfect glass, interpreted by imperfect minds, reaching towards something larger than any answer we've found so far. We're getting closer, we're just not there yet.